morning, everybody, and welcome to another edition of Talking Science with VDW, EMO, and renowned institutes of WDP, the German Academy of the Production Sciences. Today, we are going to deal with, let's say, the next big thing in automation. After we are dealing with the automation of production processes itself, now the next big thing is how can we automate manufacturing planning? And we are happy to have as a speaker Dr. Martin Erler from Dresden University, who is the head of the division for cutting technologies and its planning. And as far as I know, he's going to show us how we can close the loop and go the next step from having a manual planning as we do every day. You know, or some of you know that I'm also engaged in open standards for machinery communication. And as somebody pointed out to me, the most important tool in manufacturing planning is Microsoft Excel. So nothing to be seen about automation here. So I'm eager to learn what's the next big thing and how this can be realized on a software-based approach. So welcome, Dr. Erler. We are looking forward to hearing from you. And to all of you in the audience, feel free to ask any questions. You have a questions window in your operation panel. And when you type in those questions there, I will see them. And we are going to go through these questions after Dr. Erler has finished his talk. But now, Mr. Erler, the floor is all yours, and everybody enjoy the insights.
Thank you, Dr. Proos, for this very brief and friendly introduction, and also welcome all. Thanks for the opportunity to talk here and to present our current findings and maybe some glances to the future of manufacturing planning. I'm glad to see that so many here and are curious about the future of manufacturing planning. And my talk today will be split into 4 parts. Today, first of all, I want to go through why subtractive manufacturing is still a topic and will remain in the future. Then we will go into the planning methodology of today. After that, our current findings and approach and a future perspective of planning. Let's start low. Let's start with some facts about subtractive machining. It is still the most important manufacturing process, at least assuming that every sold machine tool is used for manufacturing. And so machine tool production is so important, especially for Germany. Another slide about that. And there is still so much to do and left. Although it has gained a lot of value for us, I want you to look at the lower right left box, and it shows that you need, if you're providing and using a machine tool, then you need to pay 1.4 hours of programming in order to get 1 hour of machining. Taking the higher wages in Germany into account, that means that you already today have to pay more for the programming than for the machining itself. So the costs for programming a machine tool exceed the costs of using it. And then there's another problem, the resource consumption. Of course, this graph shows the whole industry, metal industry, but we can be sure that by the development from 2010 to 2020, we can see that there is a little decrease, but still not enough, and there need to be something done about all those topics, especially in terms of manufacturing and its planning. Luckily, in the last decade, we have won a new technology, and that's where additive manufacturing, or 3D printing so-called, comes into play. It allows an astonishing variety of geometries and has already opened a new door to our world. But there are some obstacles. There are some problems and disadvantages about additive manufacturing. I've pointed out some here on the slide. I won't go through them in detail, and you can read on your own. And as you might know, some of them, at least we can assume, will be solved in the future. Some, at least in some sort, will remain. But then, of course, and that's where it becomes interesting, there are also three really big advantages of planning 3D printing, or so-called additive manufacturing. First of all, we now can produce parts that in the past could not be milled. So we can provide functions, properties, and designs that were previously impossible to do with milling alone. Second big advantage is resource usage. Environmental protection is everyone's business, including manufacturing technology. It not only consumes considerable amounts of resources, but also represents a central enabler for more environmentally friendly products and services through more efficient manufacturing technologies, just like 3D printing. But how? Well, planning plays a special role here, as it determines over 80% of the subsequent resource and energy requirements. At our working group, we research and develop methods and technologies to leverage this ecological potential in an economical, viable way. And here comes the most important advantage of additive manufacturing into play. Almost no one is talking about so far, right? And that is the simplicity with which the machines are programmed. Everyone who ever used a slicer in order to use his 3D printer at home maybe knows what I'm talking about. I'm sure that one of the main, if not the most important reason why 3D printers are spreading so fast is that everyone can use them almost without learning. That enables incredible short production times for single parts, independent from their complexity. If you just lose some time maybe in the printing process. But hey, that's how all new technologies have begun, right? You might remember this one, or like this one. Do you remember? In some machine shops, you can still watch such machines do their work. So CNC today and 40 years ago was well established, but was in those times and today still hard to program. 40 years ago, it was really hard to program. Why? Well, programming a machine tool looked like this. It's like today with your 3D printer, just imagine you have to program each single step of your 3D printer, and it was really hard work and required a strong spatial imagination. That's why the development of CAM software arose. And here you can see how CAM software started. It's also almost 40 years ago, and most of us were already alive when those inventions started. Today, it looks more like this. Did you spot the difference? Exactly, the mustache is gone, right. ChatGPT might have mentioned that there are still humans, and that's where I want to hook in. Why? Why can't this be changed? Why do there need to be humans? Do they? If I would have asked these questions 10 years ago, when I started my research on this topic, I would have been sent to hell directly, I guess, for doing research on how to make people unemployed. Now the times have changed. Who would have thought 10 years ago that the feared and job-destroying automation once could be the saving shore for our highly productive and developed industry that is desperately looking for workers in order to at least maintain its competitiveness? We don't need less automation, we need more. And because the machining and production itself is already highly automated, the next logical step is the automation of planning. But what is planning? Especially in terms of milling. Planning means creation of planning data, which are usually used in the next planning step. Based on this diagram, you can see where it comes into play, and depending on what you are planning, the next step can differ. If we call planning in terms of milling preparation of work, it created planning data. So planning means creation of planning data, and planning data have different requirements, structure and accuracy, and are therefore more or less easy to create. NC programming, for example, is a very time-consuming and a planning task, and also requires a lot of skills that need to be learned. which is also a very time-consuming and expensive process. But there are many other goals for preparation of work, and therefore many other planning data. Often only some of the information generated during the very complex and time-consuming NC programming process are needed. That's where our approach comes into play. Just imagine we want to manufacture, to mill this part. What do we need for, just let's say, to estimate the machining time? Most planning results can be calculated from a sequence plan. Therefore, we use different approaches. The main influence factors on calculating a part for manufacturing and the main data that can be acquired for manufacturing planning are information about the clamping, which uses a lot of time, the roughing, the finishing, and finally, putting all these three different tasks in their different distributions into a proper, maybe optimized sequence. So how do we do this? First of all, we use a plane surface segmentation method. That means finishing is creating high surface quality at the highest accuracy. Here we use surface models because finishing is about surfaces, right? So we do it on the surfaces. Our software then calculates some pseudo tool paths on the surface and heads on. Now we are at the roughing part. Roughing means removing material mainly as fast as possible. Surface quality doesn't matter, at least almost. And here we use volume models because it's about the volume that needs to be removed, right? So just take the blank, the stock part, subtract from it the finished part, and then you retrieve the differential volume. For our sample part, that looks something like this. Then we just place the finished part inside its stock part, and now the difficult part begins. By retrieving the so-called differential volume, we look at the differential volume from all different directions and calculate properties depending on this direction and the accessible tools. Those properties are now added to the volume model, each by single part. And for example, so we can show and assign possible tool size and the removable volume to this part. Our fitness function then tells us how to separate the volume into different operations. For these different operations, milling paths for roughing are calculated. And from these, of course, times can be derived. Last but not least, before coming into sequence planning, we need some information about the clamping. That's a very complicated process because clamping can be done in so many different ways by so many different tools and accessoires that it's almost impossible to find the optimal solution. Therefore, we take clamping into account, but not looking for the optimal solution. We just determine if there is a possible solution. So we do not determine the forces or the specific clamping tools that might be used. We check if there is a sufficient and accessible clamping area where a vise or something else could be applied to. So is there an area available for each operation? So now we do have the finishing operations, the roughing operations, and the clamping information, which usually, by putting them into order, results into clamping operations by turning and changing the setup. Those things are put into graphs. Those graphs represent the order of the operations, and by assigning features and properties to the nodes, we can now calculate, by following just one single path, how the machining of this part following this path, which means doing it in exact that order of sequence and operations, would cost and which resources would be needed to do so. Yeah. But if you imagine that a part maybe with 20 to 30 operations has a lot of different possibilities how the operations could be machined. So there are many different orders. And if we want to check them all, that's way too much to compute. So for example, if a part has 30 operations, you would have to calculate roughly something between 20 to 30 faculty times different operations. That's almost impossible for current computers to calculate all, so it's impossible to find an optimal solution. in order to find a proper solution anyhow, we use MetaHeuristics. MetaHeuristics just means professional and guided trying. There are a lot of MetaHeuristics out there, and we tried a lot, over 20, and we found that simulated annealing, so far we got the best results with. So putting all our operations in a proper order using simulated annealing, we finally put all these things together and added this in the little demonstrator software you're showing here. So you can see by just loading this part, the finish part and its stock part, our approach calculates automatically a sequence for roughing, finishing and clamping, assigning tools and calculating the machining time for each individual operation and the overall machining time, even using clamping areas for this part. This can be done automatically for 3+2 axis milling so far. 5-axis milling is something different, especially 5-axis simultaneous machining, because the tool movement differs completely from those in 3 or 3+2 axis machining. But how will this technique, maybe think so far, influence the future? It's not an NC programming technique, right? You are right. With this technique so far, you are not able to program a machine tool automatically. This still needs to be done by a human. But there are a lot of applications where just having this planning data is quite sufficient. Let's look at this graph here. We do have a methodology for planning on a factory or something like that. And if you look closer, you can see that here inside there is a loop. That's how most planning works today. You generate a result in the planning step, and those results from this planning step are the input data for the after following planning step, which then creates also results or states that it needs some changes in the prior step just to be able to create more efficient, more optimized results in its step. So there is a loop inside. And this loop is very time consuming. Just imagine the things between manufacturing planning and the material flow system, or the manufacturing planning and the design of a part. That's the most and best known thing everyone doing manufacturing planning knows, is that the designer gives you the part and you have to deal with it. Even if the part is really, really bad to manufacture, you still have to deal with it. And you wish that you could go to the designer and tell him, please, please, please get rid of those little radius. They are really hard to machine. And why does this whole part have to be 6.3 microns? Just for which reason? It's really hard to machine and it takes a lot of time, and he doesn't think about it. So there are rules which apply to CAD construction and designer, that they try to make parts not only be functional, but also easy and cheap to manufacture. But there's also a lot of other things that they cannot take into account because it's hard to calculate. And that's where manufacturing planning comes into play. One of our current projects, we try to use our approach to improve the manufacturing planning itself by coupling with the logistics planning inside a manufacturing planning task. Yeah. So the transportation system inside a factory is highly dependent on the way the parts are machined and how the machine tools are distributed and organized. So far, the transportation system had been planned based on very stiff and unchangeable assumptions how the production works, but that is not very user-friendly and not very realistic, because production changes rapidly, and with it the system for the transportation system itself should also. We try to couple this with a fast answering system that can provide easy information what to expect from the future by taking the parts into account and calculating the manufacturing plans for it, or at least the planning data that are needed for making a schedule for the transportation system. We've tried to focus on where this could be used, and this graph, I think, shows it very well, that there are a lot of applications beside that where an automated manufacturing planning could be used. So for example, in make or buy decisions that are usually very early in a process or a production or a product planning step need to be met, there are usually not many information available, and there are a lot of parts. Just take a car or something big into think of a car where maybe hundreds or maybe even thousands of parts at even maybe a low level need to be decided. Do we machine them on our own or do we buy them? And you would have to calculate and to do a manufacturing planning and C programming, even at least today, on hundreds or thousands of parts just to decide, do we buy or do it on our own? With the software, with the approach I've shown to you, it would be possible to do this decision just by a few clicks and get it automatically. You just ask the machine in the evening and you have the answer in the morning. You can do this once, twice, or maybe a couple of times a day. So changing a plan becomes much more feasible than it is current. Same applies to strategy decisions, to scenario calculations, to change processes, or even to investments, where you can also use to better negotiate with contract manufacturers, with suppliers, and even for soft manufacturers, it can be very interesting. And I will show you how. When you think of designing a part, there's always the problem that I've pointed already out, that the part is mainly designed by the designer, who's taking functional properties and requirements into account, not so much the information how the part or can be machined or how it fits into the production. It needs to be machined and produced later with. That's where our approach and our current project comes into play. We try to provide the designer who is creating and designing the part with future and high value information about how this part can be machined. So for example, by analyzing this part, not only by the price of the material and some plain machining times, but also the whole machining process, we can tell him, for example, that if he removes this hole, then the part does not need to be machined from an additional site, which means it would not have to be changing setup. That means a lot of saving just by putting a hole maybe in a different position. Of course, the manufacturing planner or the system itself cannot decide if the hole is necessary in this point. This can only be done by designer. But providing him with the information that this hole costs or results in an increase of 30% of the machining costs, he at least has a clue to think about how the part could be changed in order to make it more machinable. By doing so, there's also the possibility that the meeting and the process talking between both, so feedback for the construction, for the design between the manufacturing planner and the designer, can be reduced to a minimum, because most information the designer is asking from the planner can be derived from the software, from the approach we have shown to you. So there is a lot of potential time saving within such a process. So if it is implemented in the way I've shown to you as a pop-up or even a function in a CAD system, it would be possible that there is even almost no more information, human interface between the design and the manufacturing planning. There's only once the planning in the future when the part needs to be manufactured, then it once calculated the tool paths and then it can be used. There are a lot of other possible applications for this thing. So maybe thinking of instant quotes, you can also already see that there are some companies out there who are trying to do the same, but not really succeeding so far as I can see. Don't blame me if I don't want to blame them for stating wrong. So please correct me if that's not correct what I'm saying. But there's also automated machining time calculation for an application I've shown you before, automated tool demand calculation for the tool organization in a big company that has to deal with a lot of tools. That might be very interesting to know which tools might be demanded in the future. And just by seeing which parts are already in designing and under construction, they could already know which tools would be used in the future, maybe 1 or 2 weeks ahead. So they can already start supplying their own store with it. So manufacturing Copilot, you all might know the GitHub Copilot, which helps the programmer to program and shows suggestions for code or improving him. The same could be done for a manufacturing Copilot. So if you are doing a planet, the Copilot could just give you hints. Hey, you could do better here. I found a new approach and I found a good idea. You could do it this way or do it that way. Does it really need to be this way? This all could be done also for the designer. Automated factory planning. For factories where a lot of machine tools will be used, of course, it's really, really important to know how the machine tools work, how the machining times are, which tools are needed, and how the transportation between is going and which material is used. If you can plan this at least at a rough level in the early stage, that's a high advantage and a really big win for companies using such an approach. Same goes for the calculation of programming time. Programming time usually is not taken into account to the parts cost, and it's usually in the head costs subsumed, and which means that you cannot calculate easily how much programming goes into a single part. So it's hard for you in the companies to do an ROE calculation on improvements in this area, but with such thing it becomes much more easier, because you can show that programming a complex part is much more complicated and therefore much more time consuming and expensive than doing the programming on an easy part. And if you do this in calculation with how many times or many pieces of this part will be needed later on, you can do an easy calculation, which is sufficient, which is not, which brings a revenue for the company, or where does the company have to pay to machine this part. Automated and C programming, but that's far in the future. We aren't there yet because there are many other obstacles to take into account and to solve so far. There are other requirements. And improved and accelerated process chain designs. That's one of our big problems in the main future, coming together with all those new technologies like additive manufacturing. I've pointed out that additive manufacturing requires always a post-processing, but how is post-processing done? You don't know so far, but if you could combine those techniques, you could create and calculate a whole process chain for additive manufacturing and the post-processing usually done by milling. And also support on process decisions. So which manufacturing process do I need for this part? Is it better done with additive manufacturing, or is it better done with subtractive manufacturing? Of course, you all know that depends on how many parts I know, but where is the break even? 10 parts, 100 parts? With such an approach, you could easily find out. If you're interested and curious about the future about that, please don't hesitate, ask me. I will try to answer your question as good as possible. So far, I'm finished with my talk. Thanks for the opportunity. Thanks for listening. And now I'm open to questions.
Well, thank you for your insights. Again, if you have any questions, please do not hesitate to type them into the questions Fragen panel of the control panel of the tool that we are using here. Meanwhile, my question is, you showed a large variety of planning tasks on your last slide, from the actual planning of the machining process up to the planning of the entire production, including allocation of machine capacity and so on. When I said the mostly used tool is Microsoft Excel for production planning, so that's mostly capacity planning. And I know from my background that planning of machining is usually done in CAD/CAM environments. I personally see there's a disruption of the tool chains. So you do the one thing in one tool and you do the other in the other tool. Where do you see the future in combining these worlds?
Yeah, that's a really good question. It refers a little bit to my last slide and what I've shown you today. Even if it looks like a finished software, please keep in mind we are doing sign, and this is just a demonstrator for the methodology and the technique we are developing. And the developing is an ongoing process. New technologies.
Are you working?
Always.
Short question in between. Are you working with any commercial software supplier?
Not so far. Those are currently the projects we are doing are funded by different agencies and different fundings, and we are not at the state where we could go for implementation with a commercial software supplier. But there are software commercial CAD and CAM software suppliers that are within our supporting Beirat. Don't know the German English word currently, but I think everyone will know what I mean.
Advisory panel, advisory board.
Advisory panel, thank you. And
okay.
They are helping us a lot, and that's currently also not necessary because a lot of CAD/CAM software, which are growing together, right? 10 or 20 years before, we could see that there are CAD software and there was CAM software, and then they were talking about the interfaces in between. That's where IGES and all those things and STEP came into play. And now STEP never really established for different reasons. And now the software tools CAD and CAM are growing together. So the CAD software usually is buying CAM providers, and they are growing together, and they are it's just a button in the software anymore. So you're switching just with one button between the designing part and the manufacturing planning part.
Okay.
So they can keep their models inside and don't need to export them.
Okay. Another question here. How much artificial intelligence is in what you are doing here?
Oh, that's a good question. Thank you. Of course, it looks very easy, and so you click a little bit around, and then you are done. Already MetaHeuristics are considered some sort of machine learning because they are some sort of clustering techniques. We are using methods of machine learning inside our software, especially clustering algorithms, advanced clustering algorithms, but AI in terms of artificial neural networks is not implemented so far. We are planning to do so in the future, but for now, I don't see any need or usage for doing so. Because first of all, we need to implement some sort of human behavior of planning to make the planning results look more human-like. And as you all might know, if you want to use a neural network, artificial neural network, you need a lot of training data. And I asked some companies, but for some reasons they didn't want to give me all their CAD programs and parts.
I wonder why.
Yeah,
but I think this is really one of the dilemmas we have in production technology, that the variety of jobs are so diverse, and that it's really hard to get training data for all the fancy things people believe you can solve in the future with AI. Well, no training, no AI. It's usually as simple as that.
Yeah, there's also a big. Please.
No.
There's also the common problem in planning of manufacturing planning, right? Yeah. So everyone has learned how to program a machine tool, but everyone has learned it in a different way. Or even if they have learned it all in the same way, over the time they established their own way to program a machine tool. Yeah. So if you ask 4 programmers, you get 5 different times. That's how it works, and each one has a very good explanation and reason why he's doing it his way, and then they can talk hours and hours, and there's no reason, so no result who's right. And you have to admit that probably both are right and all 5 are right. And that's the problem when you come along with automated solutions. It just presents one of a lot of incredible amount of possible solutions how to machine a part. And then the planner looks at it and says, no, that's not correct. That's not how I would have done it. So they expect from the software in the first place that the software guesses how they would have machined this part. But they forget if they get the same task the next morning, the next day, they themselves would create a different solution. So if you give the same task to the same planner on 2 different days, he will not create the same solution. So he on his own will create different solutions. But from the software, it is expected that he's guessing the correct solution, as if there is a absolute correct solution for this, which does not exist.
And is there any, let's say, metrics where you can say, well, the human process designer can evaluate whatever he does and gets a score, and then you see what the automatic algorithm does and gets a score, and in the end probably the human designer can see that in some tasks the automated planning algorithm simply has the higher score.
Yeah, I think that it could be a solution how to create the change process, but there needs to be a change in how planning is done, and there needs to be a change of mindset in the people using it. I don't know if this is possible with the current generation, because they are really highly sophisticated technicians, and they have a lot of experience, and I think they have always a good explanation why the lack of this experience is really bad for the planning results. And I think they are right. But at some point, there will be the ease and the simplicity of the planning more the bigger advantage than the better result of the planning. That's the big advantage and the big power of standardization. And this comes into play when this software or this techniques like these spread over the whole industry, and some companies start taking advantage of those really short planning times and can provide services and products that are based on this. And then it's not important anymore if the machine tool is running 2 minutes or if it's running 5 minutes, if you can make it run within 30 seconds instead of half an hour. That's the important part. Especially for parts with which are produced at lower piece amounts, like 1 or 2 5 pieces, which is a big field of application and a really big use case in the future.
Okay, thanks for your explanations. I don't see any more questions here. So once again, many thanks to Dr. Oerler for his insights. And my last message to you would be that for the next Let's Talk Science edition in April, we are going to talk about additive subtractive process chains for wire arc additive manufacturing parts with some guests from Vienna University and University of Leuven in Belgium. So mark down the date. You find it on the EMO website. And from my side, thanks for listening in. Once again, thanks to Dr. Oerler. And have a great day and enjoy the upcoming spring. Goodbye.
Thank you as well, and have a good day. Bye-bye.